there's since last I met, how basically starting to doing some calculation, doing some simulations. So maybe 2 examples on that, and there is some of my previous collaboration with Harvard, the corners lab. So how we model the soft suit and how we can optimize the actuation. So then there's a few other more examples which talk about something I've been doing at NJIT, the stuff I work with the other faculties in the BME department. Okay, so one of the things I think maybe last 2 weeks, so we talked with how basically we have a normal spine-inspired device, which basically can generate the lifting force perpendicular to the torso, which is quite innovative as I can see basically. But the thing is, you want to discover, how much that affect your musculoskeletal loading. So what I come to modeling part is basically, I'm trying to model a simulation. Say when you lift a weight, which are like 15 kilograms, right? So how much muscle actuation, right? How much muscle force on your spine? And that's basically we generate motion and we do a simulation. As the color you will see basically is the muscle activation, which is number between 0 and 1. 1 means 100%. You're using the maximum. Like this bending, at the beginning, you're pretty much using all your muscle strength. So, and then we'll say, okay, let's try to model basically the device, which provided based on these profile of actuation, it's have a force perpendicular to the torso, and starting from maybe 250 Newton and goes to 0 when you get to the standing up. And we can do the simulation. As you can compare basically the muscle activation, you can see it does reduces muscle activation quite a bit, especially at the beginning. You have large basic force applied. So there's consequences here. Basically, what you can see, it reduces the shear force between the lumbars, especially L5 and S1. And because the design of the device, basically you have one section at base S1, and so that's something a little bit, you see a huge reduction, especially at the beginning. You have from 500 Newton to 300 Newton, kind of the shear force. The same thing for the compressive force, from 3,000 Newton to maybe 2,000 Newton. Okay, so that's kind of modeling can tell us, could your device be effective or not? One of the things, the compressive force, of course, comes from basically you have gravity, you have inertial effect, but what proportion is coming from the muscle contraction? So one thing we can do is basically look at the muscle. Maybe the muscle itself is coming from a model developed by Chris at Berkeley a few years back, and made some minor changes. But with this muscle model, and we basically analyze the force. We put them together, among maybe the 3,000 newtons, almost 2,500 newtons coming from muscle contraction. But again, you do see basically a reduction due to the assistance from the devices. So that's going to be basically from model. We're trying to see how this robotic device impact on human motion, and maybe in the future we can design a better actuation profile such that you can even reduce basically the muscle force more. Okay, so another thing basically how I talk about, how about squat? A lot of people are talking about squatting, right? You're squatting. Squatting is basically you do a squat a few times, your muscle contraction pretty high, especially the quads muscle here. And this figure basically showing the torques, joint torques. The muscle really what it does is trying to generate the muscle joint torques such that it can perform this motion. So this is a predicted motion. Basically, we don't have any experience, just like the previous one. And we predict the ground motion force. We predict the muscle activation. But things now, for example, if we want to design an actuation system or robotic exoskeleton and put some actuation, so the easiest way, I think a lot of times people are doing this way, is basically you just put the idealized joint torques. Say maybe the portion of it, maybe you can have a certain profile of joint torques, or maybe simply you can say, let's say 20% or 30% of this torque was coming from the actuation instead of the muscle. So what that will affect your basically your muscle force. Basically, if you compare primarily the quads muscles, it reduces just basically because we have hip and knee assistance, like 25% and 50% of torque assistance. Basically, we are just follow exactly the same profile, but with reduced amount. I think for nowadays, I think there is some other papers which talk about you design a profile which follows kind of sine and cosine kind of shape, and you can change the width. So that's something we can do as well, as long as we use this kind of idealized actuator. It's pretty, in terms of modeling, it's pretty straightforward. I mean, the main thing we discovered basically the quad muscle. Even squatting, the quad muscle is the one affected most. So you can see, compare the actuation. Actuations, we start from like 25%. This is average because the quad muscle really is a group of muscles which are performing the knee extension. So it's kind of going down from like 25% to maybe only 10% of the maximum. And we're looking at also, we are doing detailed muscle modeling. We look at the fiber contraction and found that fiber basically velocity. So we look at the energy and the metabolic cost as well. So this metabolic cost rate and the integration of the rate. So we can see how much metabolic cost was reduced. It's very good results. But when I try to do the whole body, all the muscles, it's not as good as the one, because the metabolic load coming from some of the hamstring muscles, of the other muscles like the ankle muscles. So it's going to be less reduction. I mean, it's profound reduction in intensive metabolic cost. But that's the main muscles which were reduced. So this kind of thing basically tells us basically you can maybe trying to find out a better profile of actuation and see how that affects your muscle force, muscle energy consumption, and metabolic cost. So, okay, this is pretty old stuff I did when I have a project with Conor Ross at the Harvard. Basically, at that time, maybe 6 or 7 years ago, he still have a device which is based on numerical muscles, like wrapping around human, pretty complex wrapping system. And later, I think he probably goes more to the bottom cable approach. So one solution I did is basically, it's very hard to model the wrapping itself because it moves and it's still. One thing I did at that time, basically, let's assume it's anchored to certain positions, not moving at endpoints. And so you model a few major actuators, and so you make sure when you moves, when you walk in run, basically you actually have to wrapping around your body. So the way it models really nice, it's like additional muscle in addition to your natural one. The only thing about this kind of a pneumatic muscle is it's have a certain amount of capacity of 400 Newton, but you never worry about the fatigue of the muscle, okay? You want to utilize as much as you can on this muscle instead of your natural one. So we try to put this model to run. Basically, this is the one without any actuation. So, and the really, when people do that, this kind of simulation is like you kind of tracking a motion. You figure out what the joint torque required, right? Then you do a static or you do optimization to figure out, okay, because it's always determined system. There's 20, 30 muscles around the knee to generate one unique joint torques. So the many combination of muscle torques can do the same thing. So the way you can do it is basically you can have optimize. One objective function is optimize such that you can have more muscle involved, but each muscle have less basic activation, right? So, but there is a difference now. We have an additional pneumatic muscle, which we do not worry about his fatigue. We do not worry about the, should we minimize his effort? We want to utilize that as much as possible. We can put that into an objective function such that we want to utilize the pneumatic muscle, the new additional muscles, right here. Okay, so we can put that objective function. Then we can figure out, okay, meaning we can figure out what the optimal profile you needed. So that's kind of thing, it goes to maximum pretty. So we haven't really do much beyond that, but that's something what model can do. Basically, model can help you to optimize some of the actuations. Of course, this one motions we tracked, but hopefully you do parametric simulations, or you can have some kind of profile you analyze into certain spine curve, or you can optimize those profile as well. So that's kind of thing, basically, and then from that we can see how much reduction in the muscle, the real muscle actuation. You can see it's pretty big of reduction over there. Okay, so that's pretty much some of the quick simulation we did, and I'm trying to go into something like currently I'm working at NJIT. So there's one device we're trying to do hand rehabilitation for spinal cord injury patient or maybe stroke patient. So one of the devices we did is basically we have a robotic device which is called 1 degree freedom. Marine is multiple parts, but just a train of gears which can control by just one angle. And we can model this robotics, and then we also model. So I don't want to go to too much detail. Basically, I want to present some of the capability, what kind of things we can do. So if you're interested, we definitely talk. So we model human, we model robotic. The approach we model is similar. It's robotics approach. Human joints, right? This joint is not too complicated. Just hinge joints, similar to robotics. Except it's you have muscles, which here have muscles. But the key thing is basically it's difficulty to model this kind of interaction between them. Now we have a force sensor here. We have real force sensor. Based on this force sensor, we use a mission control. I will talk about a little bit later. But in this modeling, let's say we want this finger basically follow tracking a motion, finger motion closing and opening. We see how can we do that. So we model, one way to model the interaction, basically model contact. The problem with contact is sometimes you got this continuous, force which make a control difficulty. So one thing we did is basically kind of using kind of an anisotropic or viscoelastic spring kind of thing. So make sure you don't have this kind of separation. You adjusting your parameter such that it's kind of like you've got the right parameters for sure. And we model joint friction and some other stuff. So this is one of the animation we see basically. When we tracking this open closing motion, you see the robotics follow it. The robotics here itself is purely passive. Okay, it's driven just by this force here, and also of course constraint on this top part. From there, what we see, basically you can see what the interaction force between the robot and basically the finger. It's like 4 Newton of force, and then we can also see the muscle activation because when we're doing clothing, extension probably have a higher activation over there. So now, okay, let's do a control. So we do have a mission control which was implemented in the hardware. So I joined something and let's do something in the software and trying to tune some parameters. The mission control is pretty easy. I think something your control people probably knows it's pretty well. So the key points I want to say is basically a few things. Basically, a virtual mass here. It's basically driven by this force sensor, and then move up and down basically, and then use inverse kinematics, calculate your target joint angle. So this kind of like looping here. So basically the model, what we need to do, it's basically we want to tune up some of the mass parameter, damping parameter. So there's a few things we want to tune up. So basically when we do similar simulations, the only thing is now we have this whole loop here. So we just try next 1, 0. Okay, it's very simple. We can easily find. Okay, now we reduce the force from 4 Newton to 3 Newton, just simply by doing this control. Again, now reduce to 2 Newton. But when you keep increasing those certain points, you reduce the force to 1.5 Newton, but now it's getting a little bit oscillation because the feedback PID controller we use at that. So this basically now 6 is good for that. Like you can see the muscle activation, especially the extension muscles, they reduce quite a lot. So this kind of basically, our goal is basically if you have a patient which cannot open your finger, so we have this device, we'll be able to do that. And the simulation basically can help us tune the parameter before you even do some real prototype. Of course, we have our prototype here already, but this is still something we can do. So basically, just by tuning the different parameters, how it affects things. So not much here. Another is if you didn't got the right parameter, something you got high oscillative motion. So your control is not good. So that's something we're trying to avoid when we're trying to do real hardware. And you can also provide distance. Like say, when it becomes stronger, you want this device to provide resistance instead of assistance. So very easy. You can queue up the parameter, mass parameter, makes kind of like dragging you behind. So that's kind of thing basically we can do here. Okay, so that's basically. Now let's go back to the lower leg system, which is more challenging because it's under actual system. You have foot ground contact. So one of the more that did before is usually we try to model the house system, which we found out that if you put everything together, especially angle, affects pattern quite a bit. So we did a simpler version without this angle device, but they have actuations like pneumatic or linear actuator at several different locations. So again, the difficult thing is more the interaction between the human and box. You can use Finament, but Finament, the problem is, now it's so slow, you cannot do control. Or you can use, using more like simplified Finament. You can do that still. What we found out is still, make control pretty difficult. So one way we did is we did similar things we do is like we assume there's certain, assume you have 4 sensors here, but you strap, we model strap as an elastic element. Again, it's anisotropic such that you have a larger force between your lateral movement, but you can slide easier. So this kind of parameter need to be tuned up a little bit to make sure it's kind of fits to reality. So, but the problem is I don't really have access to the device. Okay, so we don't have a hog device. And we don't have the motion capture of this device working with the human. So now what we can do, but it's still possible we can simulate that. So one thing is we can assume when you wear this device, your motion can change too much. So, and that implies like you can still track in similar motion, but now your ground reaction force is different, right? Because you have an actual 20 kilogram of weight on your body, and you can predict that. So we developed basically a loop, a kind of a tracking loop. So the unique things we need to predict ground reaction force, and it's working pretty well for running because mostly single stand space, but for double stand space, you might need to have additional optimization or additional weight distribution between that. So this is one of the simulation we did. This is not exoskeleton, but like we have motion we are tracking, but just normal running, right? But now we put actual 130 pounds of weight to that. We make sure our model can still predict that without too much difficulty. So that's basically a kind of beginning step for us to model exoskeleton, which you add actual force, add actual perturbation to the motion. So then we think about controller. Okay, this is a device. We have actuation here. So you have force sensor here. So one way is to when you measure the force, then you will say let's reduce this force. The way to reduce this force, say let's generate a counter moment from the actuation. So this is not just like actuation, like admission control, but now it's really intensive torque. So this we call minimize interference, and we can basically apply this like this. So apply this to the control loop. So another way is like and this controller you don't need to know anything about human movement. What you need to know is only about the force sensor. From the force sensor. And the second controller we say let's see we know the intention of this human. Then we know, what's the target acceleration of this human, right? So, and then if we know what target basically torque for the human, so it's good we have the force sensor will generate the force, which can generate this torque. But this torque also comes from linear actuator. So it's like chain reaction, but now we provide more assistance by knowing the basic intention. So there's a formulas I don't want to go into. So one thing basically what we did is we did simulation without any exoskeleton, basically it's baseline simulation, and we did the one with the passive exoskeleton, and 2 controllers we designed. So this is just purely virtual controller, which there's nothing implemented on the hardware, just some virtual simulation. So what we found is compared to the previous example, we see again a lot of reduction in the quadratic muscle, ENC rad muscles, which means less activation. And of course, the ground reaction force is much higher than the normal running. Sure. So yeah, pretty much. From there you can see, you can analyze a lot of things like force, spring forces, actuation forces, the profile, and some of them are, have different signs because one's just jumping behind, another one's getting in front of the torso. So this kind of thing you can analyze for sure and see how effective your controller. So last one, basically the one that we're working on basically is a device we have been developed at NJIT, Dr. Andreas from Kessler and Dr. Adamovich from the same department. So I've been here basically. One of the unique things about this model, you have an active ankle actuation. So most of repetition robot basically have either passive or fixed ankle joints. So this one have but it makes things pretty heavy. So that's something I don't like, but at least it's working. So we're trying to do control. One of the key things being do the balance controller, and we predict the motion such that a strutting motion to minimize the torque, and we're looking center mass, tipping moment, angular moment stuff. So this predict the motion, and we try to put this guy with the human, let them coordinate with each other. So one of the things we did, okay, in order to be stable, make sure your center mass have to be all within the supporting polygon. You predict the motion such that it works in sync. Now we're currently working on basically running or walking, so it's not most efficient walking yet, but that's the first step we are trying to do. We're looking at the balance, make sure it's kind of stable. So human motion not necessarily stable sometimes, okay? So this is more conservative strategy here. So we're looking at basically, again, zero moment point, capture point, center mass again, about all the dynamics. So that's pretty much like conclude my talk on what musculoskeletal instrumentation can do and how they can collaborate with robotics. And so hopefully I will find more observations on this kind of work. So definitely Dr. Zhou basically for the last few weeks in the Chronowash and Scott Delphi, I got motion from me when I have joined the project.